SwayamPrabha. Digital India. Educated India.
Hello, this is the sixth lecture on axial flow steam turbine. I'll solve some problem today illustrating the flow through steam turbine and multi-stages. The statement of the problem number 1 is the velocity of steam entering a simple impulse turbine is 1000 meters per second and the nozzle angle is 20 degrees. The mean peripheral velocity of blades is 400 meters per second and the blades are symmetrical. If the steam is to enter the blade without shock, what will be the blade angles? Part A, neglecting the frictional effects of the blades, calculate the tangential forces on the blades and the diagram power for a mass of 0.75 kg per second. Estimate also the axial thrust and the diagram or the blade efficiency. If the relative velocity, that's the part 2, if the relative velocity at exit is reduced by friction to 80% of that at inlet, estimate axial thrust, diagram power and diagram efficiency. So once considering no friction, you'll have to estimate the axial thrust and diagram efficiency. When there will be friction, then also you are asked to estimate axial thrust, diagram power and efficiency. So I'll solve the problem now. Let me first sketch the blade profile. It has been told that blades are symmetrical. So beta 1 must be equal to beta 2. So blade speed is u. So this is an impulse turbine blades. So W1 be the relative velocity and W2 be the exit velocity. So W1 is the relative inlet velocity and W2 be the relative exit velocity. This is my tangential direction theta, and this is axial direction z. So W1 makes an angle beta 1 with respect to theta and W2 makes an angle beta 2 with respect to theta direction, that is tangential direction. Now what are the quantities are given? Given that C1, that is the absolute velocity exit from the nozzle, is 1000 meters per second. Blade speed is equal to 400 meters per second. Alpha 1 is 20 degree. Blades are symmetrical, hence beta 1 must be equal to beta 2. Mass flow rate to the turbine m dot is given as 0.75 kg per second. So these are the quantities given. Now let me draw the velocity triangle. So this is U, blade speed. W1 be the inlet relative velocity to the rotor. W1 and U would result in CU1. So here I have indicated all the angles with respect to tangential direction. So hence this is beta 1 and this is alpha 1. Blades are symmetrical, that means W2 will make an angle beta 2 that and here beta 2 must be equal to beta 1. So this is suppose W2 and W2 here will be K into W1. So in reality when there will be friction, W2 is less than W1. But without friction, when you neglect friction, then W2 would be is equal to W1. In this case, K is equal to 1. In this case, K is less than 1. So this is my C2. So let me take another color. So this angle is beta 2 and this angle being alpha 2. Please note that beta 2 and beta 1 they are equal, as I have told here. This is C1. I have forgotten to mark. So I have completed velocity triangle now. Now I'll solve the part 1. Now here K is equal to 1. So friction is neglected and hence W2 is equal to W1. Now from inlet velocity triangle, CZ1 is equal to C1 into sine alpha 1 should be equal to W1 into sine beta 1. Further, let us consider C theta 1. C theta 1 is equal to C1 cos alpha 1 so I am correlating now C theta 1 with W theta 1. Okay, so C theta 1 is equal to W1 cos beta 1. W1 cos beta 1 is equal to W theta 1. This is C theta 1. That should be plus U. So C theta 1 is equal to W theta 1 plus U, that you can see from velocity triangle. So now I can say this is my equation number 1 and this is equation number 2. So from 1 and 2 I can write, so let me go to the next page. From 1 and 2, equation number 1 and equation number 2, I can write tan beta 1 is equal to C1 sine alpha 1 divided by C1 cos alpha 1 minus u. This you give equation number 3. Now here C1 is known, alpha 1 is known, u is known. So all quantity in this is known. So what is the C1? Just to make you, so that for your appreciation, C1 is 1000, alpha 1 is 20 degree, divided by 1000 into cos 20 degree, u is 400 meter per second. So one can solve beta 1. I have solved beta 1, I got the value of beta 1. Please check the numerical value, 32.36 degree. So this is the value of beta 1, that must be equal to beta 2. So I have solved the blade angle. Now from equation 1, I can say W1 is equal to C1 sine alpha 1 divided by sine beta 1. C1 is known to you, and so alpha 1 and beta 1. So if you evaluate, you will get 639 meter per second. In this case, this also would be equal to W2, since K is equal to 1. After getting W1 and W2, I can calculate del C theta. Del C theta is equal to C theta 1 plus C theta 2 from velocity triangle. Please refer back to the velocity triangle. So this would be equal to W1 cos beta 1 plus W2 cos beta 2. This must be equal to twice W1 cos beta 1, being W1 and W2 being the same, and that's beta 1 and beta 2. So if you calculate this, you will get 1079.5 meter per second. Thus I have evaluated del C theta, which is C theta 1 plus C theta 2. Now del CZ here should be equal to CZ1 minus CZ2. Now since the blades are symmetrical and W1 and W2 are equal, hence I can say this must be equal to 0. So there will be no axial thrust here. So I can say axial thrust is equal to 0. Now let's come to the tangential thrust. Now if I denote tangential thrust by PT, PT would be equal to m dot into del c theta. Now I know the value of m dot, that is 0.75 into del c theta. Just I have evaluated 1079.5. If you evaluate, this should be 810 Newton. So I have evaluated the tangential thrust. Now what will be the diagram power? Now diagram power would be equal to diagram power is equal to W dot. So W dot would be equal to PT into U. Tangential thrust into the blade speed, that must be equal to 810 into 400. So this I have got around C to 4 kilowatt. So I've got another answer, right? So I have evaluated diagram power. This is the tangential thrust, and axial thrust is 0. Now only remaining now is diagram efficiency. So let's go to the next page to evaluate diagram efficiency. So diagram efficiency would be that is blade efficiency eta B should be equal to W dot divided by half m dot into C1 square. That must be equal to C24 divided by half into 0.75 mass flow rate into C1 square, that is 1000 . Now this W dot here, this is in kilowatt, so I'll divide it 10 to the power minus 3. Okay, so if you do that, this will be 0.864, that is 86.4%. Thus I have got diagram efficiency, which is blade efficiency is 86.4% when the friction is neglected. I'll now solve the part 2, that is B. Now here K is given as 0.8. So W2 would be K into W1, that is 0.8 into 639. If you calculate, you would get 511.2 meter per second. Hence del C theta would be equal to, now considering the velocity triangle, W1 cos beta 1 plus W2 cos beta 2, beta 1 and beta 2 are equal, so it would be W1 plus W2 into cos beta 1, and thus I have calculated W2, so 639 plus 511.2 into cos of 32.36 degree. If you do the calculation, you will get 972.5 meter per second. Thus, I have evaluated del C theta considering friction. Now, tangential thrust PT is the tangential thrust I've indicated earlier, would be equal to m dot into del C theta. That is m dot, we know 0.75 kg per second into del C theta is 972.5. You will get 729.4 Newton. Thus now the tangential force would be 729.4 Newton. Definitely there will be axial thrust now, since CZ1 would not be equal to CZ2, as if you refer back to the velocity triangle, you realize that W1 and W2 are not equal. Hence the CZ1 would not be equal to CZ2 here. Thus we'll get now axial thrust. What will be the value of axial thrust? That means CZ1 minus CZ2 into m dot. So that will be W1 minus W2 into sine beta 1 into m dot. You know all the value. So if you solve this, you will get 51.3 Newton. Thus, we'll have now a axial thrust that will come on bearing. Now, what will be the diagram power? Diagram power I denoted as W dot is equal to PT tangential force into U, right? If you solve this, you know the tangential force, you know the value of U, so you will get 291.76 kilowatt. So now the diagram power has got changed. So similarly, the diagram efficiency will also change. So what will be the diagram efficiency or the blade efficiency eta B? Equal to W dot, that we have evaluated earlier, half m dot into C1 square. Now W dot we have evaluated as 2 91.76, half value of m dot is 0.75, C1 is 1000. I'll multiply by 10 to the power minus 3. So it will be 0.778, that is 77.8%. I like to tell you that with friction, now blade efficiency has decreased. This is the second problem. The statement is an impulse steam turbine has a number of pressure stages, each having a row of nozzles and a single ring of rotating blades. The nozzle angle in the first stage is 20 degree and the blade exit angle is 30 degree with respect to the plane of rotation. The mean blade speed is 130 meter per second and the velocity of steam leaving the nozzle is 300 meter per second. Part A, taking the velocity factor as 0.8 and the nozzle efficiency of 0.85, determine the work done in the stage per kg of steam and the stage efficiency. If the steam supply to the first stage is at 20 bar, 250 degrees Celsius, and the condenser pressure is 0.07 bar, estimate the number of stages required, assuming the stage efficiency and the work done are same for all stages and that the reheat factor is 1.06. Let me solve the problem now. What are the quantities are given? Alpha 1 is given as 20 degree. Beta 2, that is relative exit angle of the rotating blade, is 30 degree. U is equal to 130 meter per second. That's blade speed. C1, that is velocity from exit of the nozzle, is 330 meter per second. Now here you note that it has not been told that blades are symmetrical as before. So beta 1 here is not equal to beta 2. Furthermore, there are frictional effects. So K is given as 0.8 and nozzle efficiency eta N is 0.85. So these are the quantities unknown to us. Now let me draw the velocity triangle. So first I'll draw the inlet velocity triangle and then I'll superimpose on it exit velocity triangle as before. So this is U, blade speed, W1, and this is C1. This would be tangential direction. theta. This will be axial direction Z. All angles are referred with respect to the tangential direction. So hence this is beta 1 and this angle is alpha 1. After that, let me draw the exit velocity triangle. So W2 here will be less than W1. So this is W2 would be equal to K into W1 and this should be equal to C1, C2. So this angle is beta 2 and this angle is alpha 2. Note that, let me mark the component. This is CZ1, axial component of C1, CZ1, and this is CZ2. Now here CZ1 would not be equal to CZ2, so most probably there will be axial thrust since W2 and W1 are not equal. Furthermore, considering inlet velocity triangle, this is my C theta 1. That is tangential component of C1. This is C theta 1. Similarly, this is W theta 1. So C theta 1 and W theta 1 I have marked. Furthermore, if you take the exit velocity triangle, this should be equal to C theta 2. And C theta 1 plus C theta 2 is del C theta. Thus, I have completed the velocity triangle. Now I can write from inlet velocity triangle, that is CZ1 is equal to W1 sine beta 1, that should be equal to C1 sine alpha 1. Now let me put this equation number 1. Furthermore, I can write W theta 1 should be equal to C theta 1 minus U from velocity triangle. So I can write W1 cos beta 1 should be equal to C1 cos alpha 1 minus U. So this is equation number 2. Now from 1 or 2, I can get tan beta 1 is equal to C1 sine alpha 1 divided by C1 cos alpha 1 minus U. Here I know the value of C1, which is T30 meter per second. I know the value of U, that is 130 meter per second. I know value of alpha 120 degree. So put all the values here and you will get beta 1 equal to, please recheck the calculation, I have got beta 1 is equal to 32.075 degree. So now look, here I have calculated beta 1 and beta 2 is given. Therefore, you know the blade angles. Again, from equation 1, I can write W1 is equal to C1 sine alpha 1 divided by sine beta 1. I have calculated the value of beta 1. I know alpha 1 as 20 degrees, C1 is 330. If you put all the value, you will get W1 as 212.54 meter per second. After evaluating W1, I can get W2 as K into W1, which you will get 170.03 meter per second. As I know W1 and W2 and beta 1 and beta 2, I can get del C theta equal to W1 referring to the velocity triangle cos beta 1 plus W2 into cos beta 2. You know the value of beta 1 and beta 2, you know also W1 and W2, put all the values, evaluate, you will get del C theta as 327.35 meter per second. So hence work done per kg of steam you can put that is W as U into del C theta. I have calculated the value of del C theta as 327.35. You know the value of U as 130. If you multiply both, you will get W as 42.55 kilojoule per kg. So I got the work done per kg of steam for a stage. Now the blade efficiency, eta B, I'll get del C theta into U divided by C1 square divided by 2, kinetic energy of jet. You know the value of del C theta, you know value of U, you know value of C1, which is 330 meter per second. This is actually twice W divided by C1 square. So if you do that, you will get eta B equal to 0.7815. Thus, I have got blade efficiency as 78.15%. Now this is the blade efficiency, not the stage efficiency. That is efficiency of the rotor. Now let's go to the next page. Now let me evaluate stage efficiency. Stage efficiency eta S is equal to blade efficiency into the nozzle efficiency. I have evaluated blade efficiency. Nozzle efficiency is given as 85%. So if I evaluate stage efficiency, it becomes 0.664. That is 66.4%. Thus, I have got another answer, which is the stage efficiency 66.4%. Now I'll go to the second part, part B, where I'll consider multi-stage turbine, and there I know the inlet pressure as 20 bar and 250 degrees Celsius, and the exit pressure as 0.07 bar. Now let me draw the HS diagram, enthalpy and entropy diagram. So this is S and this is H. This is saturation line. This is the constant pressure line. Let's consider this is P1 is equal to 20 bar and P2 being 0.07 bar. Now let us consider the expansion now. So this is 1, 2 be the actual expansion, and this 1, 2 is be the isentropic expansion, 2s isentropic. So entropy at the state point 1 must be equal to entropy at the state point 2. But in the actual process, which is 1, 2, that is a non-isentropic process. Now, let's go what is given. Now, let me first consult with the steam table. As per the steam table, for 20 bar and 250 degrees Celsius, the steam is superheated, so I can read H1, I can read S1, enthalpy and entropy. I got H1 value is 2902.3 kilojoule per kg. Now, I got the value of entropy as 6.5466 kilojoule per kg per K. Now, I do not know what is the state of steam at the end of expansion. That is, what is its dryness fraction, or whether it is supersaturated. So what I have done, I have gone to the saturation table, and corresponding to 0.07 bar, I've got HF, HFG, SF and SFG. HF I got 163.16 kilojoule per kg. I am not writing. HFG is 2409.54 kilojoule per kg. SF I've got 0.5582 kilojoule per kg per K, and HFG as 7.7198. Let us consider the isentropic expansion. Let me put S1 is equal to S2 isentropic. Now considering even the value of SF and SFG and also S1, one can imagine at point 2 there should be some wetness value or dryness fraction. Now let me evaluate dryness fraction from this. So S2 isentropic can be written as SF plus X into SFG. Now you know the value of S1, you know the value of SF and SFG, and thus you can evaluate X. Thus by solving these I can get X is equal to 0.7757. As you have got X, you can calculate H2IS, that is enthalpy, at the end of isentropic expansion, which is HF plus X into HFG. And I have got this, please check the calculation, I have got this 2032.30 kilojoule per kg. That's what I have done here. I have considered inlet pressure and exit pressure, which is a condenser pressure. From steam table, I have got the value of H1 and H1. Considering isentropic expansion, I have calculated dryness fraction at the end of isentropic expansion, and from there I have evaluated enthalpy at the end of isentropic expansion. Let us consider now eta 0 be the overall efficiency of the steam turbine. That means considering number of stages. So eta 0 should be equal to now eta S, which is stage efficiency, into rate factor. I know the value of rate factor 1.02. I have evaluated the value of eta S. So if I do this calculation, I have got eta 0 as 0.77041. That is 70.4%. Now from definition of eta 0, I can write is equal to H1 minus H2 which is the actual expansion, divided by H1 minus H2S. So eta 0 is the ratio of actual expansion through multi-stages divided by ideal isentropic enthalpy drop. So again, let me say eta 0, the overall efficiency is the ratio of actual enthalpy drop divided by isentropic enthalpy drop through number of stages. So from there, I can evaluate H1 minus H2, which is nothing but eta 0, you know the value of eta 0, into H1 minus H2IS. I know the value of H1 and I know also the value of H2IS. So this is known, which is in the bracket. So I can get H1 minus H2, which is the actual enthalpy drop, as 612.57 kilojoule per kg. Right? So what will the number of stages then? Let us consider n be the number of stages. Then n would be equal to del H, actual enthalpy drop, divided by del H per stage. Now del H per stage is nothing but U into del C theta, that we have already calculated. So this would be equal to 612.57 divided by 42.55. That should be equal to 14.35. Number of stages cannot be a fraction, so it would be nearest whole number, n would be equal to 15. So I have solved the required number of stages, which is equal to 15. I have solved two problems on steam turbine. Hope this will help you. Thank you for listening.